very much my pleasure to introduce Michael Bartling from Arm Research. About a year ago, I was at SOSP and chatting with a very good colleague of mine at ARM, and I was telling him about some of the work that we've been doing to try and infer meaning from signals that we were getting from systems. And my friend said, oh, well, you know, I've got this researcher, an ML guy, who does this really cool tracing work and can detect all kinds of fascinating things. And of course, immediately, the hairs on my back of my neck stood up. ML, oh, okay, whatever. I'll listen. But then I actually met Michael. Went, oh, like he's an actual ML person that understands systems and doesn't hope to just throw ML and hope that something just pops out the other side. So it's really been fun to work with Michael because Michael has a deep appreciation for defining the problem and expressing the system's components in a way that you can actually make meaning of the ML in a useful way. And we've been having a ton of fun hacking the last couple of days. So with that in mind, Michael, it's all yours.
Yeah, I guess I'll give a little bit more background to myself. My name's Michael Bartling. I've been at Arm Research for about 9-ish years now. My background is in formal machine learning and surprisingly enough, security and embedded systems. So in fact, I built one of the first TinyML frameworks called microtensor, which got me in trouble and also landed me in Arm Research. So a lot of the work that I've done has been really around how you not only use ML, but how you basically coerce it to do things it was never meant to do on systems it was never meant to run on. And so with that in mind, a lot of the parts of this presentation, when I'm talking about models, I am using ones that perform well as proxies for much smaller models that I know can run on these devices, and I have shown them. I just don't have a lot of examples of that data in my charts and graphs because they're just more tricky to get just right. So it's like, why go through the effort until you really need it? So what is the Akira project? Really, it started out as this idea where hardware is extremely expensive to tape out. It's really immutable once you've taped it out. And security flaws are always present. Hackers always find some way of exploiting anything that you've ever made. It's basically a waiting game before they break into whatever you design. So can we build something that sits on the processor, is able to understand the software behaviors that are running as they execute in this complex system, and just reason on that? And ideally, if you can reason on that, you can catalog these behaviors. You can stomp out the sketchy stuff, or you could potentially retune the processor to be a little bit faster for things that you do care about. So let's go forward a little bit on that. So right now, in terms of defenses, there's really only a handful of options at a very, very high level of what you can do to keep attackers from doing things that you're not expecting. We have architectural features, things that most of these try to target very specific types of attacks. So memory safety, isolation of processes, things like that. They usually cast extremely wide nets for very targeted attacks, but they also have a decent amount of overhead, whether that's in runtime or the cost involved with developing them. It takes a lot of time and effort to make these things and make them just right, and even more time and effort to get people to adopt them. Because a lot of times in security, the problem you run into is you say, oh yeah, we were able to do all this cool stuff, and then say people ask how expensive it is, and then you go, and then they don't want it. They'd rather have something that's fast. So the next main common method is probably the ones that y'all are familiar with on your systems. Those are static methods. McAfee, they scan your binaries, PDFs, anything you download. They look for just signatures of structure that represent attacks that you might see or any sort of sketchy behaviors, and then they just throw a flag or throw an alert. And these are very good at what they do. They're very low overhead. They've been around for forever, but the problem is they're very easy to get around because sometimes you can exploit just the structure of software itself, and things that look benign in nature are actually malicious. For example, compression looks benign in nature, but someone compressing your entire hard drive and throwing away the key until you pay them money is not benign in nature. So these are the sorts of things that kind of break that entire methodology. And then the current trend is for these dynamic methods, things that look at behaviors or actions over time and try to just figure out if the chain of events are sketchy or benign. The problem there, the biggest problem, despite being able to potentially catch anything and everything, is they're either really expensive or they're extremely data driven. And anyone who's ever tried to run a malicious sample that's more than 1 week old, that's already a losing battle. These things tend to fail the moment that they've been released. Even getting representative benignware, examples of software, you think it'd be easy to just run a GUI application and press a bunch of random buttons. No, it's actually fairly hard. So getting a large enough data set to exploit in a diverse way with machine learning tools is a challenge in and of itself. And that really sets the bar for what your models are capable of doing.
So I said, why is it hard to just have a GUI and have some monkey process that process things?
It's not just having one, it's having a bunch of them. And also being able to go the chain. So if you like open your phone, you just want to go through settings, how many levels deep do you think a monkey hitting random spots on the screen is really going to be able to go? Is it truly playing the game on the screen? Is it really typing in information? Maybe modern ML methods and agentic-like views could potentially fill in those gaps, but that's still an open problem. But ideally, if you're able to solve that problem, get a big enough corpus of these dynamic traces, then ML will just blow up in the right direction. And that's kind of the hope at this point. You're starting to see in more fields, models being able to do labelings, do data extraction, build these data sets without with off-the-shelf tools versus human intervention. And that's kind of where what we're trying to do with this project is automate that process some. So I'm going to actually skip over the hardware-backed security bits. And really, like I mentioned before, hardware is frozen when you tape it out. You don't get a lot of options to patch a security flaw once it's there. And usually when you do, there's an overhead involved. And you'll start seeing older hardware performing worse and worse over time, not just because the hardware is degrading and modern hardware has gotten much better, but it's also because you have these different patches that have to be sent to hardware that now force it to behave in a slower fashion, just so people don't accidentally compromise your system and steal your photos or your bank accounts and stuff.
So, Michael, just a quick question. You have references to Cherry there. Do you mean like the Cherry processor?
No, the Cherry extensions for memory safety. It's basically that's memory tags and I believe capabilities for just trying to make sure that a particular region of memory is not accessed by someone who shouldn't have access later. So, long story short, there's something missing in hardware that really makes it behave like an immune system. Like, what if we could create a fixed cost piece of hardware and a fixed cost processing pipeline that's able to consume this software, and maybe the model can be updated over time? Can we react to emerging threats, and can we react to software behaviors? And then once we have that, what could we do going forward? What does this enable when you have this sort of hardware level software introspection? I mean, ultimately, it's very tricky to do these sorts of things because hardware in and of itself is not monitorable. When you start looking at how PMUs operate under the hood, you realize there's a lot of noise and there's a lot of fine tuning just to get a signal that is meaningful. And you also, if you're building a system like this, you need to be extremely careful that the measurements that you are making are generic enough where it can apply to different architecture or different microarchitectures. You want one model to rule them all. You don't want to have to worry about all of the hacks that engineers put in place to make a system faster, because at the end of the day, an ISA is there to say, oh, from a software level and above, this is what I would expect to see. Under the hood, it can do whatever it wants to speed things up or slow things down or exploit parallelism and so on. If your measurements are susceptible to that, then your model is not going to work well when you try to deploy it to a new device. You want to make sure that you're trying to capture a generic form of what exactly the software's intent is doing. So it's got to be a little bit careful. And here's our fundamental asymmetries that we're working with. Attackers only need one exploit to actually work, or an exploit chain, while defenders need to stop all of them. This makes sense. This is just the nature of the game. Attacks, but this is the really important one. Attacks are extremely rare in nature. Almost everything that you're looking at is benign. So what any sort of methodologies you come up with have to have extremely low false positive rates, because you do not want to affect performance. It is better to not put your tinfoil hat on. It's better to try to just do a best effort here and catch as many things as you can and not worry about what you don't catch. That's really what differentiates some of this work from a lot of the state of the art. We're looking for false positive rates of 10 to the minus 9, not false positive rates of 20%. And then, of course, the adversaries are dynamic. They can change their methods at any time, and hardware defenses are immutable. So, evolving the state of the art. When I said 20% false positive rate is the state of the art, I meant it. It's actually, it seems like this is reasonable when you do ML work. A lot of times you see, a 20% misclassification rate. That's not too bad. All I'm looking at are cats and images, but this is running at gigahertz rates. So once every, actually about 20 times per millisecond, you're throwing an alert, and your system's performance is going to tank. You really want to do it maybe on the order of once a second or once every other second. At that range, you can filter. So you have a lot more wiggle room for getting around the detection threshold. And if you start thinking of why this is the case, here I have an example of a program that's running in a steady state. But because the processor that you're running on has other things running at the same time, it's got potential boot up bits for the process that's going to run. Another program might be running at the same time. You might see a warm-up state. And if your ML is trying to learn, in this case, it just learns the threshold. Anything above that might be considered program A in its detection. Well, if I have a second program that has this warm-up state, from here, it's just not sure exactly what it's detecting. So in reality, if you put another program before it, you could put it into a noisy state, and your ML just doesn't know how to account for that, because you have not gotten that diversity component of all the complexity of modern software systems being measured on this device under test. I'm going to skip over that slide. So our ultimate philosophy, assuming we can't catch everything, what can we do to make attackers' jobs as hard as possible? And that's where we come into the reactive security component. This, I realize on this screen, is a much smaller than it's on the normal places that I present. But we have a couple of main bits that we're going to try to detect. We have a local detection policy. This is something that's going to be extremely lightweight ML, mostly a retrieval-like system for labeling behaviors as they come in, and potentially giving those and running on or near core. And given those labelings, it might run some basic mitigations, and those mitigations may be issued in an order to try to leak more information about whatever behavior you're looking at. I'll get into that more later. Then we have a tiered approach on top of this. We'll have additional logic and additional models that consume these higher dimensional summarizations of behaviors and try to look for correlating patterns over time in sequence and see if it's evident of a chain of attack. Because the more information you have, specifically over time, if someone's doing sketchy things once, twice, 3 times, then you have a lot more information to work off of than one thing in isolation. It looks more like noise. So what does security sensors look like? As I mentioned before, we're looking for things that don't necessarily represent the microarchitecture, but more represent what the software is going to try to do. This could be things like network timing. It could be CPU events, performance events. And in our case, we have limited our study to performance monitoring events, not performance monitoring statistics. So we can try to capture time as it's changing throughout a system and the sequence of behaviors that map directly to instructions, such that we can try to get this high level view of what software is trying to accomplish. But there's a lot of options for building security sensors. We have a few ideas, but really this is still an open area of research. I mentioned we already have our tiered response. So let's take a look at what we've actually built and what the data looks like. We have instrumented Gem5 to, for the PMU specifically, to output raw trace events as they occur at a cycle, not fully cycle accurate, but at a cycle, active cycle ID in time. We have the ability to window in software just high-level labels of regions that we know we care about. This could be a phase of a program. Say it's if we're looking at zip, it could be deflate followed by or level zip followed by a Huffman encoding. These higher level views, or if it's an attack like Spectre, we can mark each individual component that we care about and just see if we're able to detect those as a higher level view. Then additionally, we track which PID is running so we know what program is actually leading to something. We built a PC trace, also correlated with the same active cycle timestamp. So now we can go and attribute all of these labels to the exact piece of code and the exact instruction that generated it. And then we can start building up these high-level mappings and make sure everything makes sense. And for workloads, we've tested on a number of things. I think it's something like 150,000 total, both benign, mostly benign programs in user space and system space. And we have limited most of our study to benign programs because they are, one, easier to run, and two, under test, we think that we'll get a better representation of arbitrary software behavior with that. And then hopefully, and when I tested this against Spectre, it shows up more anomalous if you're careful about how you do your feature extraction. Now, the feature extraction is the real secret sauce to all of these ML methods. And if you try to run off-the-shelf DSP methods or off-the-shelf, or just throw this time series directly at ML models, you're going to blow up either in bandwidth or you're not going to really capture the representation under signal. So that's where these path signatures come into play. It's an idea that was originally used for studying stochastic differential equations. And all it's really doing is looking at how, if you have, say, you pick up your phone and you're moving it in space and time, or you're drawing the letter A with your finger in space, this motion is trying to be captured in a lower dimensional, well, ideally infinite dimensional representation of the path, the motion over time. And they're really cool because they're very robust to distortions. If you write the letter A 5 times, you're going to write it 5 different ways. If you write it slower or faster, it doesn't really matter. It forms the same signature. But the letter A still maps to effectively the same path signature, even under those distortions. It's time invariant, or reparameterization invariant to time, and it's also translation invariant. And when you think about it in terms of what an attacker might do, that means that if they try to hide in the noise, it's harder for them to do that because the most likely things that they would exploit are slow down their process, introduce delays, or try to hide among other bits of code so that they appear as if it's benign in nature. And then actually, if they do that, it becomes more evident that they're trying to hide with this sort of methodology. But the best, when you look at some of the other mathematical properties of them, they're pretty cool. But the most important part of all of this is that they're extremely well suited to hardware. In fact, we've come up with hardware blocks that can build these in a streamable fashion in about 100,000 K-gates, which is, by today's standards, a rounding error. So we think that we can get these thrown into actual hardware near core and eventually be able to get real measurements and not just hope for the best. So what can we do if we have this system? Let's start by seeing if we can identify higher level programs, algorithms. So we started by training a model. In this case, it was XGBoost. But like I said before, I have another methodology built on locality sensitive hashing that is well suited for hardware. It's just basically hash functions that you run a bunch of times, and it does very similar things to this. So hand waving things away. The performance that we're going to see on these next handful of charts is going to map very closely to the behaviors that we saw for these. But we get a better apples to apples comparison if we use the exact same model with similar hyperparameter tuning bits. So we trained a model to recognize gzip versus bzip2, just two different compression algorithms, specifically on an audio file. And then we tested it on tar of the same two algorithms, just adding a little bit of scaffolding on top, and wanted to see if we could detect a text file. And we found that without any real hyperparameter tuning in extremely small versions of this classification tree, we were able to show distinct, even for large windows or small windows, you can distinctly identify the bulk of these two higher level programs. And if you switch the order of the file, so you're training on a text file versus an audio file, the performance actually drops. And that makes sense too, because the audio file is a lot more complex in nature. It's going to express more code pathways in the higher level programs. And you won't see those if you train on the text. So if we're able to train on things that are more complex, then we get more diverse or models that are better able to generalize. So can we get any finer grain than that? Let's see if we can identify kernel functions as they're operating in Linux. So we ran this, most of this study is on the Linux testing project. It's basically meant to stress test Linux in every corner of its little dark cloister. And we found that we were able to distinguish over 1,000 different kernel functions, the most common ones, with about 85% accuracy here. And that's more like a ranking thing than true accuracy, with extremely short windows. But importantly, it's not just that we were able to get this accuracy, it's that accuracy, those detections were stable over time. So almost all of the labels that you would see, yes?
So quick question. Identifying kernel functions, for a given kernel image, I only need one sample to be almost 100% accurate. I just look at the program counter and where the kernel image is mapped.
Yeah. I know you can. This is just to see if these models can determine the higher level behaviors that are happening through the kernel function. It's not, this wouldn't be useful for detecting the kernel function. We think that there's behaviors that kernel functions are doing that could be grouped later into specific labels. And the ordering of those labels are describing what those kernel functions are doing over time. That's what we're trying to get to. For now, we're just using this as a proxy to get to that point. Can we even understand these shorter order meta behaviors?
How hard would it be for a malicious adversary to generate the same kind of paths?
Actually, combinatorially hard. So because we're doing PMU events, even if you just limit yourself to 2, I'll talk more on this a little bit later. If you limit yourself to just instructions retired and branches, the problem becomes just a simple combinatoric of number of instructions plus branches that I see for a window, choose the number of branch points that I have, and those are all the possibilities that an attacker could have to yield the same counts that you would measure for one of these windows. Now, spoiler alert, the number of usable instruction sequences relative to those branch points is actually extremely small in comparison. So they're pretty much screwing themselves if they try to do that process because it's already
It's obvious that they're faking it.
Yep. So you can exploit those probabilities when you're doing a lot of the your final classification, or at least doing the calibration, and that makes the life a little bit easier. And there's other tricks that you can play to screw them more, but that's outside of the scope of this this presentation. So yeah, actually, if you look at the labelings that we get over time, assuming that these are just looking for the behaviors of the kernel functions, not necessarily the kernel function itself. Again, we're using that as a proxy. Those labels are stable as you make your predictions. So almost the top graph over there is showing that pretty much every single labeling was maintained between one window and the next window. And this is a multi-label case, so there's multiple windows there, and they just move smoothly across. It's very rare for you to see one window that just jumps to a completely different label. It happens, it's at the boundaries, but what this is implying is that our 25 sample windows are shorter than the most common length of function that you might see in the kernel. The kernel functions are generally more than 25 instructions, approximately, for a specific boundary, and some of the behaviors are evident across multiple of them. And when we try to generalize this into a true multi-label set, I ran this particular experiment on one big ass trace captured from the Linux testing project, and wanted to see if just training on one trace, would I be able to get a model able to label, multi-label these windows from all of the other traces that I had. And it turns out for about 90% of the available traces, that holds up. This is actually just sorted based on the trace ID and the index. And what we're really finding is about 5 or 10% of the traces have behaviors that are not evident in that one big ass trace. That's how we read this. But if we're just trying to identify top 60 kernel functions, or the behaviors that are in these top 60 kernel functions, or the mix of them, we're able to do that pretty confidently. And of course, this actually works even better when you try to reapply this to user space code. And this additionally makes even more sense because the compiler in and of itself is trying to do as much code reuse as possible. You see a lot of these underlying behavior or instruction sequences showing up even for two people writing the same algorithm. They might get slightly different code, but a big chunk of it is still the same. And that makes it even easier to detect or differentiate user space behaviors. And again, this is with 25 event long sequences. Now, I don't have this plot in here, but I run the exact same experiment on basic blocks. We thought that basic blocks, because they are these fundamental units of execution, and there's a limited number of them, then we'd be able to build a corpus of at least the chain of events of these basic blocks that could truly describe what software is doing. And I found that the performance went almost all the way up to 100% on that. But again, that's very early.
Actually, Michael, just from a security perspective, just so I understand, so I guess that plot there. So the attacker runs the same analysis and figures out the bottom 1% of functions, the rarity ones. Mm-hmm. That would be the set that they would try to hide.
That would be the set that they would, yeah.
So the game would be, is your coverage relative to that ability for somebody to computationally find that the rarest ones, and therefore start to.
Yes, it's that. And it also means that from a defense side, we have a good indication of the ones that are not our most commonly seen set. So they can either have two paths, look at the most commonly seen behaviors and try to use that to hide the noise, or look for the ones that are rare and are not as detectable and use those to try to hide the noise. But because they're going to be going through a sequence of behaviors, this is all still the local detection stuff. This is just, can I see the behaviors that I expect to see and label them? When you start looking at it as a chain, it becomes harder and harder and harder for them to truly stay undetected.
Compromise your module.
We're screwed. But the idea is this module is running in a secure, effectively a secure enclave near core, and there's pretty much no way to touch it outside of the injection path for a new model. So usually when you actually look at most of these models for retrieval, the part that breaks it the fastest is the distance function that you use for the retrieval metric, whether that's inner product or cosine distance. If you always return 0, then it's always going to fail. Sure. So really, as long as you lock that down, you're good to go. But the basic block analysis, here's the really, really interesting part that we ran into. How many unique basic, out of 150,000 experiments and dynamically run traces, how many unique basic blocks do you think we ran into? And that's just instruction, options, and ignoring all the register bits. How many unique basic blocks do you think we found? Millions? Billions? Or pretty large code. Some of we had Geekbench 5 and we had spec in our data set. Would you guys think it's a lot?
It's a plus. Just based on the question.
Yeah, 18,000. I found 18,000 unique basic blocks that represent all of the software in our corpus. It's almost nothing. Those are all the labels that we would need to care about to build up a language. Yes.
You're talking about static or dynamic basic blocks, because it would seem that you want to label them statically, but they look entirely differently dynamic.
What do you mean by that?
The static notion of a basic block can give you
We're not doing JIT.
What?
We're not doing any JIT stuff.
No, I'm not talking about JIT. I'm saying if you're looking at it purely dynamically, you get a different solution for what is a basic block because you don't see jumps that go into the middle dynamically.
Oh, yeah. No, we're not doing that. We're only looking at relative to a PC points, which basic block we're in. We're not looking at the jumps between them. So as we're running through our code, we know we have a PC value. Pre-static, like in statics. Offline, I go and compute a unique ID, static ID for each of the basic blocks of all the software that I've got. Keep only the uniques, and then from a PC point, I just make sure I jump into the basic block I see, I rehash it, and then I get my ID from that, from the lookup tree, lookup data structure.
How far do you know dynamically to go where to hash it? You're somewhere in the program, you're hashing dynamic functions to get your ID. How far are you going? How do you know you hit the end of the basic block?
Oh, no, I'm just saying, am I in that exact basic block? So it's that PC value, I know which program I'm running. And I have this trace. So offline, I just reload that program in PyElf tools. I have the PC from the PC trace. I know my offset from main because it's not, a static executable. It's the dynamic loading relocated nonsense. I jump over, post all of that, figure out exactly which basic block I know I'm in. Then that's when I hash and I use that as the label. So a window is a multi-label set of these basic blocks over time. That's how that analysis is set up. We're not looking at the jump points. We're just looking at where are we currently. Yes.
So if you have a small set of basic blocks, that seems to be very useful for classifying against malicious code. But how does this behave on a system that generates new basic blocks like just-in-time compilers or a developer workstation?
That's a big open question that we have. We have not had the time to actually look at just-in-time compilation, but we're interested to see if it yields a lot of the same low number of possible basic blocks relative to all of the ones that you might see. And one thing that we did notice is user space code tends to have smaller ones than system space. I mean, that makes sense too. You're more likely to see optimized loops, things that are unrolled, things like that.
Michael, the same argument that we talked about with the functions would apply here too, right? So if you found out that 18,000 basic blocks roughly covers your corpus, then it also means that whatever's rare or JITted becomes now a more additional game to play, right?
Yeah. I mean, it won't have labels, but I mean, that's still one of the goals of ML is to either assign new labels or really in this case, it's what kind of mix do I think I see? Early on, I mentioned we're not trying to catch everything. We're just trying to catch as much as possible. So under those conditions, at least we know we have a good idea of we can handle non-JITted code. I would have to, again, run the same sort of analysis on anything that was JITted. Ideally, actually, ML models, because they in inference, because they do have a lot of kernel issuing and so on. And when I say kernel, I mean the ML kernel, not Linux kernel. So that might be a good proxy. But yeah, out of all of the possible combinations, there is a very small number of, in that noise, the small sequences of code that actually do anything meaningful. And within those, there still be some data dependence. And we think the data dependence is what actually signifies the most information of what a program is actually doing. Not the static code, the ones that have dynamically changed based on a user input or whatever it's processing in code path. So if we try looking at how these models are behaving on sequences of those code segments and just trying to classify the next one, we find that most of the mix in this is like most of the main class, the top class is very, very easy to classify, the one that you're most likely in. And the mix is where a lot of the noise comes in and where it becomes harder and harder to truly gauge if you've made a clean decision at that first local stage detection. But that doesn't mean that a second stage can't try to filter this out. So let's look at the second tier classification. We started from an unsupervised view of the world. Let's say I don't know what any of the behaviors possibly are. Let's just assign 10 labels to them, 50 labels, some number of letters in my alphabet. It doesn't really matter what the size of the alphabet is. That's a different problem. And let's treat a trace as a string of these alphabet pairs over time. can we learn a function that can decorrelate these alphabet strings and be able to technically, ideally generate them, but more, you can think of it kind of like a deconvolution function for how they link together in a graph-like view. So we applied a graph neural net. I believe this one was graph deconvolution on it, trying to see if we can reconstruct the transition frequencies between these known behaviors and known sequences of behaviors. And more specifically, if we'd be able to actually see those labels show up in a two-dimensional projection. And we found that these models were very easily able to identify behaviors that were locally structured and spread apart. And from that, we think we have we can build up some pretty low effort sequence analyzers to truly tell if you're doing something malicious or benign. An example of which, earlier I mentioned that those labels don't tend to change too disjointly. They're relatively stable. So you can just build first order moment classifiers on that, just trying to make sure that you're not seeing a lot of those discrepancies. And that's pretty much it. We did, another one that's not on here. For shits and giggles, we ran a transformer on raw data and found that it was extremely, extremely expensive because transformers are, but the pass signature representation of it, one of the tricks that you get with them is what we call the depth, how much information in the tensor that's output that truly captures the input sequence. And as we increase the depth of this these pass signatures through a simple classifier, an MLP, we could approach the same performance that a transformer could get on the raw data. And transformers, the reason why we think this is a good comparison, internally, they're actually looking at how two samples are pairwise attentive to each other. And if you have a deeper and deeper transformer that's able to do more and more of these, then you get it in its own learning. It's able to find a lot of the same patterns that the pass signatures do for 1,000 times cheaper, 1,000,000 times cheaper. But I don't have that plot up here. Yeah, any questions? Yes.
So on your last slide, I believe you talked about this allows us to distinguish malicious from benign functionality. Do you have a definition for either?
Definition. Yeah, it's actually a really good question because, and it's not benign functionality, it's malicious or benign intent.
Oh, that's even better.
Yeah, I know it's hard. It's tricky. It's tricky. So earlier I mentioned that compression, if you're using it benign, I mean, in any case, compression is technically a benign operation. But if you are just compressing an image or a series of images, that's a benign action.
Yes. There's a side channel there.
There is a potential side channel, but if the most common case is a normal user sitting down, they have an image that they've just taken a picture of and it's compressed and saved on their phone. most things are benign. For most of our belief, almost all code is benign. The rare case, the one that you see very well at scale frequently, but in isolation infrequently, would be someone trying to encrypt your entire hard drive and like use that as a just ask for money. Yeah.
Okay. Let me pick up on this. I love this example because I chose it myself, right? In some other work. Yes. So encrypting your data, ransomware, awesome, right? The only difference between a ransomware and the user encrypting their data is who holds the key. It's the only difference.
How much you're encrypting.
Yeah.
What?
How much you're encrypting. Usually encrypts one file or two files.
Well, I mean, if they encrypt
not the whole drive.
Says who?
Yeah, what if they have access to your password manager? They encrypt just your password manager, like double
It's
encrypt.
entirely legitimate for me to encrypt all of my data, right? The only distinction is who holds the key, me or the bad guy. So what in this distinction between me and the bad guy, biologically two different people, we're in the US, company can also be a bad guy. What in that distinction manifests in your PMU events?
So in the PMU events, because we're looking at that tiered view of behaviors, we can correlate certain behaviors with knowing that we're doing the what's called the compression itself. You'll see that. You might also see, not long after that, network behaviors in your sequence. Our second level classifier is not going to tell you, oh, we know that this is potentially doing a threat and an action against you. We're just going to flag it as yellow, like, oh, we quickly saw a compression. We might see network, and that could be them actually taking the key, even though they're more likely just going to throw it away. I'm just using it as a crap example. But when you look at global IDSs and not just IDSs, the more modern way of people like seeing which files have been opened on which computer, which files have been moved between which computers, which system calls have been called. They're able to correlate a lot of that information, get a rough gauge if something sketchy is kind of happening. It's not a perfect filter, but you get a better idea. We're trying to build, one, the ability to detect known easy things for cheap, and then maybe also be able to add to it over time. And two, be able to add additional labels that these tools higher can reason on, and then say, oh, we have one compromised device, lock it down.
So to extend that example, and correct me if I'm wrong, because this might be far too glib, but a knife is a knife. I could be chopping vegetables with that knife, or I could be committing murder with that knife. And the truth of the matter is, like the compressor, sure, it can be used for multiple things, but the more I learn a model, and if I can extract that over time and provide more and more context, you're hoping that ultimately the murder use looks different than the non-one. Now, of course, there's always an arms race over how much I can pretend, but at least this acts as a building block to provide contextual learning around multiple timescales.
That's part of it. And then there's also some attacks. I mean, that case is tricky. The taking over your computer case is a bit tricky because it's just such a fine granularity of what actually defines the malicious versus benign nature of it. But a lot of the ones that do end up occurring, say you're looking at a gadget chain, you will see a sequence of benign events or things that look approximately benign, and then slowly over time you'll see a sequence of things that seem a little bit more sketchy. Or if it could be a microarchitectural attack like Spectre, and I'm going to just use the original Spectre v1 as an example here, even though it's predominantly stomped out. The side channel that is enabled through Spectre, you can actually, if you think you might be seeing it at this sort of level, you can run a mitigation as a test to build information about the behavior under test. Just pulling flushing part of the cache or pulling a couple of these knobs and levers will affect the behavior that you measure or expect to measure of the behavior you think you see. And if you see the response that's expected, you have higher confidence of the measurement you might, like your original guess. And you can also tier up these mitigation / experiments in terms of cost to try to get more and more information if you want. But again, that only covers a certain subset of the underlying attacks and underlying threats.
I have a more technical question. You had mentioned that to do the path signatures, to compute them, use something from algebraic topology.
Mm-hmm.
What is that something?
So these were a series of Chen's identities. They're so Chen's identity for iterated integrals on population statistics is basically this high-level path signature. What it's trying to do is just take all of the piecewise linear functions that you use to describe a path over its individual dimensions and integrate them over the various combinations.
So you're not looking at topological properties.
Yeah, we're not looking at the topological properties here. This was a tool that stemmed from topology to understand SDEs, because SDEs are really tricky. And that paper is 400 pages deep. So I don't recommend going too deep into it if you don't have to. But the main thing is, because it's all these piecewise integrations, it means that you can stream it forward. And that's, again, one of the main reasons we liked it, plus the basic properties once you actually start playing with the math for reparameterization, variant, scaling, predictably, and the translation invariance, key ones. You can also make them more sensitive to time and specific channels, but that's more a use case thing than anything else. Yes.
Which PMU event features are most useful for detecting different classes of attacks, and which one would you add?
So on which ones I would add, that is a question we keep asking other architects, and they always say, oh, we'll get back to you. But the ones that tend to leak the most information, cache misses, instructions retired, and branches that you've seen. Those three are the big ones. Which op level you're in, surprisingly, not that useful. You think, oh, being in system code versus user space would tell you a lot, but it doesn't really change much over time. So it's more interesting when you look at it at the boundary. But a lot of the other base, we only have 5 opcodes in Gem 5 currently that we can work with. So those first 3 are the most important that we found. Yes.
So you build your thing in Gem 5. The awesome thing about Gem 5 is that it does exactly what you want. So you have your PMU events that you stream out to your off-core or near-core silicon. How confident are you that whatever your ARM people build you will not lose events from your PMUs?
I'm an ML person, so I hope. That one's a prayer for me.
Good. Yeah, because your competitor does not make any guarantees about that. Right? They say we'll lose PMU events left, right, and center. And they're okay with it because they're not built for that, right? They're built for debugging stuff.
We actually, so my other colleague on this project, he's hacked into debug trace to try to get these exact events. And even then, it's still pretty noisy. But I did a quick experiment trying to figure out how different the real traces were from our simulated ones under the similar conditions. And it was really, really tricky to do because you have to make sure that the time series is scaled the right way and at the same start point. But I found that as I started adding more and more bits of information, the dynamic time warping with them converged to a point. So I think we at least have good evidence that this might be representative of real hardware. And based on my discussions with some of the architects that we work with, it shouldn't be too hard to at least feed this through the pass signature in the high fidelity form. But again, yeah, it's a prayer on my side.